All right. Yes, I think I'm audible now. We can start again. I had a few technical issues because of which my streams have been, well, I deleted them and then there's a little bit of a discontinuity. I did two things mostly. One is moving both app state and miscellaneous data, mist data, into their own files. And second is this set of operators. Okay. So we're going to look at app state just once. Nothing special. We've just moved it here. We will change how it works. We will change how it works on the other hand. I will just finish this up, which is weird. And UA 32T height. So this becomes the new width and the new height. And app state here takes as input UA 32T width and UA 32T height. Right? That's it. All right. This should be fine. If you go back to Blaze, it will require us to just add width and height into the SDL app init here. Other than that, so far, so good. So what we want is we want to get an allocator so that we allocate all the memory up front and then we can make things run as we go. Mostly for two reasons. One is it gives us a way to track how we are allocating things because a new or a malloc won't tell us that we've allocated it, while our role allocator gets all the calls and therefore we can see it. Second, okay, it's not a true reason. It's the fact that because we control allocations, because it's fast, like it's special purpose, we can do it much faster because we specify the allocations based on what we want to do, but that's not really important. Speed of most general purpose allocators is good enough for most things. The biggest reason why I control my own memory in this is locality of reference. I can put different objects within a dense area, let's say, right? So if I allocate 7 objects in system 1, then 7 objects in system 2, then 7 objects in system 1. In a general purpose global allocator, my first 7 objects in system 1 and the second set of 7 objects in system 1 will be differing from each other by 7 objects, which are taken up by system 2. But if we use custom allocation, what we can do is we can just at the start say, okay, this big chunk is system 1. And now system 1's all allocations will be within that zone. Most of the times when we do any kinds of operation within this game, each system will operate on its own, and therefore having things in the cache closer together, having pages closer together will make the overall program run a bit faster. There are talks about this that you can check out by John Lakos. There's also a few more, but John Lakos's CPPCon talk is great about this. Anyway, so that is why we have a custom allocator. Also, it lets you constrain the memory, right? So if you're on a PlayStation 5 with 16 gigabytes of RAM completely between GPU and CPU, you can limit your RAM usage to around, let's say, 12 gigabytes so that you still have 4 gigabytes for the GPU or, other configurations, whatever is more optimal for you. Okay, so these are just convenience literals. We wouldn't look much into that. We just create a struct. We call it memory. So it's just a plain struct. It will have nothing but plain old data. std byte is a little bit of it's an enum. So I'm just going to use car. Unsigned car is uint 8t. At some point, I will probably rename it, rename all of these, but for now it's fine. uint 8t. So we take data, right? Or memory, if you want to call it that. Then we will have a size t, which is capacity. how much can be stored, and another size t, which is available. How much do we still have left? This is going to be a linear allocator. So I'm actually going to call it global memory. It will only allocate. It will never deallocate. Anything you allocate in the global memory will stay until the end of the program, which makes it very simple for us to, write the algorithms for this, because every time we allocate something, the memory pointer moves forward and it never comes backward. So we don't care. Okay, I'm joking. It does come backward, but we'll look at that when we need to. For now, let's just assume that it doesn't move backwards. Okay, so global memory, it will move to have an initialization, which takes a size t of size. It can be a constant here. And for now, we'll just malloc this or new this. I think I use new. So we do a new uint 8t. It's an array of size. No problems there. Similarly, void destroy, which takes nothing. It destroys the memory. So that would be delete. And we will take the memory so that it becomes null pointer, right? Available equals 0. Capacity equals 0. Again, here we need to set those. So capacity equals size and availability equals size. Okay, so those are just init and destroy. We now need to allocate the memory. That's not too difficult either. So first we take uint 8t pointer. What a pain with this. I will actually type def this thing. So using byte equals uint 8t pointer. It's probably going to scream at me for naming it byte. I also do not care about that. Okay, fine. Byte it is. So byte and byte, right? Byte. Okay. Oops, did I make it a pointer? I did make it a pointer. All right. So byte pointer. Here we say allocate. Now allocate can require two things. First is the memory itself. So size t const size. Okay. How large do you want the allocation to be? Second is size t const alignment. Okay. And we will create two overloads for this. So you can actually have a default argument saying alignment equals 0, but doing an overload like this is nicer because first the size allocation, plain size allocation with no alignment requirement is simple because we take memory. Okay, we say byte pointer ret val return value equals memory. No problems there. Memory plus equals size. So we just move forward. Available minus equals size. And we just say there's less available to us and we return the ret val. Of course, before we do this, we assert saying, hey, do we have enough size? Now, another thing of this allocator is this will not see much dynamic allocation as it happens. Okay. So if we're going out of bounds, there is something wrong with our code is the assumption here. So an allocation should deliberately fail if you try to do this. So if size is greater than available, we have trouble. Wait, assert that size is less than available, and we can say not enough space available. Of course, there's other growing allocators. We can replace it with a growing allocator later if required. For now, we can leave it like this. Second, the one with alignment requirements has a bit more of work to do. First, we need to calculate how much memory we actually need to store, right? So based on where the data is, which is a pointer, we need to convert it to something that is not pointer. So that would be a uint ptr. That's an unsigned integer as large as required to store the given pointer in it. We take memory into it. We'll have to reinterpret cast it because this is not a static castable thing. We're casting from a pointer to a value. Okay. So we get the address. Now, for this address, we modulo it with the alignment. This gives us the found offset. So uint ptr t found offset equals that. So found offset will either be 0, in which case our memory is already aligned and we don't have to do much. We just go to the allocate version. So if found offset equals 0, return allocate found offset. The system will probably inline this. Otherwise, if it's not equal to 0, then we need to offset a bit. So how much do we need to offset? The answer is alignment minus found offset. So that is the correction we need to have. Offset. So this is the actual offset we will need. Then the next thing we will have to do is take the memory. So return value that's byte pointer ret val equals memory plus offset. Okay. So it moved by that much. Second, since we already know the offset, total size is not equal to just size. Instead, total size will be the size plus the offset because we're actually expanding the allocation a little bit so that we can have the aligned parts within itself. So size t. Oh, hi there, Dicefinity. Size t is allocation size. So allocation size equals size plus offset. Return value is fine, but available will reduce by allocation size. Similarly, memory will increment, so it will move forward by allocation size. And we will return ret val just like previously, right? Again, there is an offset, there's an assert required in this. The assert will be here. So after we have the allocation size, we will just assert saying size less than equals available. Or in reality, this can be a funny thing to do. So we let the assert happen through allocate. We can make return value as offset plus allocate, and we can just give it allocation size. Okay. What will happen here is it will just allocate the larger size. It will do everything as required. And we will just offset it by as much required to gain alignment as we need. That's it. Okay. Yes, there's definitely more niceties we can add here, but this is simple enough. This is easy to understand. We will leave it as it is. All right, so what's next? Once we have this, we just need to initialize it. So in app init, hold on. First, we need to actually add this globally. We'll put it inside a namespace. So call it Blaze Globals. Make a global memory object. Call it memory. It's a global thing. So we say G _ memory to be clear about what it is, even though there's the namespace is behind it. G memory dot init. Let's say for now, we will try with 128 kilobytes. And if required more, we can increase it over time. That's iterate, that's app event, wait. So after deleting app state, we will now uninit the memory. So again, Blaze global G memory, destroy. All right. Okay. So moving on, that creates and destroys memory. If we run it, it should just be all right if it compiles. Nope. There's an assertion failure. Something is in the wrong place. Ah, yes. When we created this, this is cleanup. This is creation. We did a miss data init, but we never initialized miss data. So in reality, miss data equals new miss data is something we actually need to add here. Similarly, in cleanup, so not here, but in cleanup itself, miss data cleanup and then delete miss data. This will be removed soon, almost immediately after, but for now we will leave it, as it is. Coming back, build. All right, run, triangle is there. So far, so good. Let's start allocating things onto our allocator. So that's global memory. Done. App state. Okay. Here, this is the first place where we want some allocation to be done. We will allocate the memory. So pointer p app state equals, this one is, what again? App state. Now we need to allocate that much. So blaze global G memory dot allocate. The size required for this is the size of app state. Alignment required from this is a line of app state, and that will give us the memory for the app state. This is just memory. It's not initialized yet. So to initialize it, we need to say new star p app state. Okay. This is a placement new operator. We are not going to use it most probably because app state is something that can fail in its initialization and something that can fail. We want to create it with a creation function later on. But for now, leave it as it is. Build should be fine. The destructor, since we're using cleanup, we don't have a problem. Otherwise, you need to manually say like tilde destruct, which we don't have a feature for. This memory will winked out, as I said, so we don't need the delete anymore. In fact, it will crash if we try to delete it because we never allocated it using the global allocator. Triangle is still working. Okay. Now, upstate here in the constructor, as you can see, we just abort, which is not entirely clean. So instead, we will add a function called create app state. It will take an app state, a pointer to an app state, right? And it will take the constructor's requirements, which would be the width and the height. So you int 32t width and you int 32t height. That's that. That is how it should look. It should return an error value. So what is the error value in this particular case? One possibility is an SDL error, which is just a printout value and a Boolean false, or a render device creation error. That is a possible VK error. But again, we print those errors from their original location. We don't particularly have much requirement to know whether something completely failed or not. So we will just say Boolean, right? The C++ way of doing this, like let's say idiomatic C++23 way of doing this, we need to use std expected, which is similar to the Rust result type. So it will either return an app state or it will return a result. We use a pointer to app state because it makes our life a little simple, simply because we don't have to bother with allocating it in here. We don't need the allocator, right? We just need a pointer to the object, and We just allocate everything we need within that particular given space. So create app state, we copy all of this, move it into here. Of course, this will be an error. So app state, window, app state, window. That gives you an error. Instead of aborting, this will return false, which will signify an error. Then make unique. We will remove this soon enough. We leave it in for now, for a little bit, but we'll remove it soon enough. App state, window. This gives us a render device, which is again app state, render device. Okay. The render device is in it. Sorry. Uh, Do we take app state as a pointer then? There's always the option of not taking app state as a pointer, taking just the memory and using it like that. I think I'll do that. I will allow that. So global memory, we don't have access to it here. We will have to add the access to it. Now it says forward declaration, but we are in the CPP file right now. It's appstate.cpp. So we need to extract that particular class out. We go to base CPP, go to the memory thing up there. We take the global memory from here. Okay, got it. No problems. Project, add new item. So it was just class. Call it memory. I think we call it global memory. Add it, done. None of that is required. We just add this here directly. Byte doesn't exist here, so we'll just say U8 So using byte equals U8 CSTD8 has to be included. Take. So those come from macro-util, and that's that. Global memory has been added. Nothing's in CPP file, everything is in the header, but we leave the CPP file in. And now this can actually take a global memory. This will be used as a reference. It won't be an out value. So it is this. We'll just call it memory. This will be an include. Create app state. Control control path return a value. This will return an app state pointer. All right. Now, first thing, memory, allocate size of app state. So it allocates as much as it will be required for an app state. Pointer app state equals. Okay, done. Cannot initialize it with byte. So we do static cast, app state pointer. Should be good to go. Reinterpret cast. All right. We have a reinterpret cast. App state is created. Window is here. We don't care about that particular problem there. Return null pointer. That's one way of saying not initialized, is we just return null pointer. Render device, this will fix itself soon enough. So this particularly needs app state to be initialized using a placement new, because otherwise the constructor will never be called. So app state, and if I'm not wrong, this constructor itself will return. So hold on. That's going to be a little bit of a thing. We create a default initializer there. So this constructor itself, does it return us a value? Auto x equals. It does. So we don't actually need the casting up there. And we can just have this as auto pointer allocation. Then we just get it to allocate, right? So this allocates a pointer place. This will use it to initialize, and we can move on from there. That's a placement initializer. Okay. Now, when the device is in it, this we will fix at some point. For now, it's just going to be used like that. Same with state miss data. Miss data, we'll do a thing, which is we'll allocate this on auto pointer. We already have an allocation, but auto pointer risk data allocation equals memory dot allocate risk data size of, so to a size of miss data. That's how much we've allocated. So here we can just say, okay, you take the miss data allocation from there, and you're then free to init that particular thing. Take render device. This will be app state render device. Okay, cleanup. Now in cleanup, there's a delete miss data. We don't need that anymore because the allocator will just pop everything out of existence for us. We don't need that because the definition is default. And so far, so good. Okay. What we will do, however, is destructor exists, a cleanup. Actually, we won't do it. We'll leave the destructor in. Can be made const. That shouldn't be, because when you clean up miss data, this should be a take, right? Render device, that should be another take. Window, that should be another take. It should clear itself out, so this shouldn't be enough. Now, add a return statement, and this one at the end returns the app state. So we're fine, okay? Otherwise, we haven't finished allocation, and therefore we don't bother with it. Okay, now we can make that a constant, we can make this a constant. So far, so good. App state is fine, but this doesn't exist in the interface. So app state.h doesn't have that function. It needs to be added, and it's added here. Global memory. We will forward declare it. Don't include anything that you don't need. Okay? Now, the nicer way, or the more, let's say, clean way of doing things be to remove the default constructor from here, to add an SDL window pointer, a render device pointer, and a misc data pointer. And get the constructor to just init the window to the window, the render device to the render device, and the misc data to the misc data. Cool. This means it can't be default initialized. Nobody outside of this particular function will be able to initialize it correctly. And we can then just take it here. This window becomes again an SDL window. So SDL window pointer window. No harm, no foul so far. Okay. We can move the allocation down here. So if it fails, no problems. Even though it doesn't matter. Takes it, does a window, returns null pointer if nothing is done. Render device. So that creates a unique pointer. Instead, we will convert it to a normal pointer. This becomes new render device. Takes a constructor. We remove the create info because now we're aware that it's the constructor. It will automatically be able to cast it. So we don't need that. We will, however, allocate the memory. So risk data allocation. Okay. And instead of list data, this will be render device. This will be render device allocation. New render device on this allocation. App state is gone. Render device gets allocated there. And we're to go from here. And we'll see, we'll actually nest it in to a certain extent, and this will slowly devolve into a few levels of passing the allocator in. But for now, we are okay. Misc data pointer, misc data init. That doesn't fail. So no problems about that right now. Render device, we take a reference. Now app state can take render device, window, render device, and the misc data as constructor parameters, and everything is fine, right? All of this now is effectively allocated on, well, not yet. Now it is all allocated on our allocation. Can we check? So we can check this by taking a render device and creating an array of bytes. Let's say, okay, we do have a byte. Okay, it's declared outside, so we can't use it directly. Uint 8t, so that's a byte array. Make it an array of 1024. That's 1 kilobyte. How much memory do we have? 64. 128 kilobytes. Global memory is incomplete because we never included it here. Width and height, it doesn't need that anymore. Doesn't need that either. So app star p app state, so that pointer equals create app state memory, which is nothing but Blaze global G memory. Width is width, height is height. That creates this. Assert, or actually, if p app state, but not star p app state, then return STL app failure, and our fate time's there. Otherwise, we can cast it and we can start using it. Poop. This is fine. Now here we have 128 KB. Let's make it 128 megabytes, or 128 megabyte, why not? And inside render device, here, this data, we don't know, in the edge file, we can say we want this byte array to be 128 megabyte long. Lovely, megabytes is not a part of this. So we'll do 1024 times 1024. Delete. When the reference in long function has been removed. Seems it all. Resolution, run. Okay. Assert has failed because we asked for more memory, which means render device is being allocated onto the allocator. Cool. This is fine. Now what? What is the next step for this particular thing? STL vectors, these will also do their own allocations. We don't want that. So we will use plain swap chain images. But here's the thing, right? At max, most implementations of Vulkan will ask for will give you 4 swap chain images. You can ask for more, but it will never be more than, let's say, 6 or 8. So a render device may ask for more memory, but it will never be more than 6 or 8. All right? Render device creation can fail. So this It's not the way to go. And therefore, we create a new function. Render device pointer, render device, create render device. So this takes render device, create info, post ampersand, create info. It also takes memory. Memory, global memory, make it a forward declaration, and call it men. All right. Create a definition. And we move on and speed this thing up a little. So mem, this will go through that entire stack up there. Vulkan initialize all the way down to this point. It initializes the frames. Move that into render device. So now we have Vulkan initialize here. Volt load instance with an instance there, which it can't find. So we need VK instance, and we're done with that. So there's instance, surface. So that's VK surface, VK surface KHR because it's an extension. Device in queue, physical device in use. So VK physical device, in use, UN32T, direct U family index. All right, there we go. That part is fine. It now needs a device. So again, outside the same set of brackets, we need VK device, and we'll need the VKQ. So VKQ, direct Q. Okay, what's next? Swap chain extend. We can directly make this auto. Oh, yeah, of course. VK extend 2D. That's swap chain extend. This is swap chain format. Is it inside that? It is inside that. So VK swap chain format. Chain format. VK format undefined. So we initialize it to that value. And we need swap chain. So is swap chain a part of that? It is. So VK swap chain KHR. Swap chain. That will handle itself. We leave the views for a little bit. Okay. And we'll get to the constructor instead. So if we look at the render device, it takes all of these, and all of these shall now be inputs. So far, like from here to here, they shall all be inputs for the constructor. Kept, be formatted. We will leave it in. You don't need explicit anymore. Leave the definition, we generate the definition. We say that, initialize all initialized members, and we can start filling things up here. It's pretty simple. Right? So swap chain format, swap chain extend. We've got all the values from the outside. We merely need to copy them in. Only the instance needs to do a little bit of work. Who does that? Right? This can be a little bit of pain sometimes. We're keeping everything as a struct. Everything is public. That's a temporary thing. We will eventually make things private to come up with a proper interface that is accessible or not accessible depending on what needs to be done. But for now, this is it, right? I'm just going to add all the constants required. Done. Okay. So what's next? Render device is created using this constructor now. Create render device is the one that handles things. So at the end of create render device, it needs to return a pointer. We will comment this part. Oops. We will comment this part, the frames right until after swap chain. And we'll return from here. So not return, first we'll allocate. So that's data pointer, byte pointer, memory, this is called allocation. So allocation equals lem dot allocate size of render device, a line of render device, new in the allocation render device, which takes instance, surface, physical device in use, device, direct queue family index, swap chain format, swap chain extent, which I can't see, swap chain extent. What a long thing. And this we return because at this point there is no failures possible. This needs its own level of formatting, doesn't it? It's you can't really call it a trivial constructor, but it is in a sense a trivial constructor. Okay. So with that, we create those particular parameters, but we haven't finished everything. So here we used to use the vectors from, STD, standard template library. So we have STD vectors here. We can't use those as they were. Swap chain image count. So swap chain images takes image count null pointer. So far, it's fine. Here it says swap chain image size. I don't particularly need that. Tries to resize here. So swap chain images don't have a resize. They say this is VK image. Swap chain images. It's a pointer because it will be an array. This is all plain old data. So we actually don't need to care about it. This can just be allocated and casted. So from mem, we'll allocate that much memory. We will size it to size of VK image multiplied by swap chain image count. So this is just like malloc. And we will reinterpret cast it. Done. All right. And then we'll get swap chain images. There shouldn't be any problems here right now. Okay. Now for the views, same thing. This allocation, we will copy it. Instead of image, it will be image view. Swap chain images will be swap chain view. And Image count will still be the same. Here we'll just size of image view. This wouldn't change anything because both image and image view are pointers to underline types. So they're all 8 bytes on my platform. So while you shouldn't hard code 8 bytes, it wouldn't care if we made a mistake here. But it's better to be clear, right? Now, image views dot reserve, we don't need that. We will lose out on this for each. So instead, so it's U32T R equals 0, I not equals swap chain image count plus I. So that's, manual for each. Image becomes swap chain image is I, right? And swap chain image views dot pushback becomes swap chain image views I equals view. And to that extent, I can move that there. Okay. So far, so good. Now, there is cleanup in this that is required, but I will leave that for later. Failure handling. There's another thing that we use here, which we don't support currently, which is, you see, vectors. These are not permanent. So having allocations for these that are permanently stored is pointless, because any allocations that we do in our current allocation model just stay until the end of time. Instead, we want these to be dynamic. However, we don't know the size of it. So, they're dynamic because we don't know the size of it, but we also can't have them, allocate on read like they are right now. So what we will do is inside global memory, inside the mem, we will create a new function that allows us to temporarily allocate memory. Or in other words, we will have struct, inside struct called state. Okay. What this state contains is a byte of memory and size t of remaining. So what is the state? Every time we call for get state, so we can put it here, state, get state, and this returns, so this is actually called because it modifies nothing. This returns a state which contains both memory, which is the current memory of the location, and the remaining, which is the current available. I should call this one available, right? And that's it. This has to be no discard, but it's not necessary. I should discard it. It's not a big deal. But then we also have restore state, which takes a state by reference because it can be by reference or by value. I particularly can. Restore state, which asserts that first memory is greater than state dot memory, which means we are ahead of that location or at the same location. And it also asserts that the size or available is less than or equal to state dot available. These are trivial. This is just trying to see, are we behind this particular point? We don't want to revert to a state that is ahead of the current location, right? So imagine if you save a state, then you save a second state, which is ahead of this state. Then you revert to the first state and then you try to restore the second state. We don't want that to happen. And lastly, we also need to check if the state came from this particular array or not. That one is a little tricky. So this particular part is 1/2 of that. We can actually put it here. This particular part is 1/2 of it. It checks if the state is within the lower bound of memory. The other one is the one that checks if memory, if the state is, so this one checks if the state is behind the memory. We need one that checks if state is ahead of it. So memory minus capacity minus capacity plus available. So what will this do is capacity minus available is how much is used. So this is how much is used. Memory minus how much is used will take us to the original starting point. And the state of the memory has to be, sorry, less than equal to, has to be state dot memory, right? So memory has to be ahead of the starting point. Dot of allocator. This is not necessary anymore. Okay. So that's a restore state, and all it will do is it will take memory and it will assign state dot memory to it. It will take available and assign state dot available to it. All right. There is a slight catch with using this. If you do a temporary allocation in the middle of this, it will break everything. Okay. Temporary allocator in this particular system is a bad idea. Sorry, permanent allocation within this system is a bad idea. And there's no way we can change anything about it. So this is a flaw of using this kind of a method. It's a known bug. We will document it. So do not do any permanent allocations after calling this. Call this before permanent allocations. Because there's some real smart thing you can do, but no point in making things all that complicated. Because here's the thing. You go through this much. So far, everything is fine. At the top, so we've not allocated anything here. This is the first step of allocation that we do, right? I will just say these are within this scope. So I can just make my state within this scope. Auto state equals temp alloc start equals mem dot get state. Okay, that's the temp alloc start. This is not something we're doing anymore. This is equal to mem dot allocate the physical device count multiplied by VK physical device size of, okay, and no, that's not alignment, multiply. Okay, so it allocates that size. We need to reinterpret cast it to the correct type. That's it. No need for data here. That's a temporary allocation. Same thing here. Again. Hello there. Mem dot allocate size of VK Q properties, Q family properties times how many did we allocate in the vector? We did not allocate in the vector. Oops. It resizes here. So it takes from this, it resizes here. does its thing, goes back up top. So I did that as a slight optimization there, which is it shouldn't need to reallocate. And what I'll do is I'll just get an allocation. So this is a temporary as well. So we will create a temporary auto temp alloc physical device. So what are we trying to do here? Physical properties. So temp alloc q properties equals mem dot get state. Again, this is another temporary state that we create. So this will continuously like go forward and back on this particular allocation. So Q family count, we take it here. This is resize. This goes away. We take Q family properties pointer, Q family properties. It's sometimes too much to write, huh? Size of. We take Q family properties. I'm just doing whatever programming I'm doing and I'm talking about it. I'm not really teaching here, so I'm not that different from a lot of people that live stream. It just happens to be code. Okay, that has allocated it. We finish this here. State is done. So this loop, at the end of this loop, we want to restore the state. So mem dot restore state, and we give it the temp allocate property. If we don't do this, no problem. It will keep allocating things in order, like continuously. And we will just have to remember to, oops, this is in the wrong place actually. This wouldn't have, well, this would have just as well. So this allocates from here, and this temp alloc start goes all the way here, and we will free it at this point. So restore state, temp alloc start, right? And that allows us to create like these short-lived zones, like a stack on the heap, okay? It's just our linear allocator that can do a little bit of stack allocation on the front. All right. Now, this creates device in queues. Do we have any other vectors left here? So vector, we have some in the surface calculations. So out here, we will do another temp alloc. So auto temp alloc state start equals mem dot get state. And the vector has to go away. So again, vector format is a pointer. Surface format count will tell us what the size it means. Allocate size of declare surface format chart counted and multiplied by the alignment. Oh, not alignment, sorry, multiplied by surface format count. Again, reinterpret cast so that it's correct typing. Remove the data from here. That's it. This auto goes here. So this is where we will restore state. So mem dot restore state. And we put the temp alloc start. So good to go. Okay. Any other vectors? Present modes. Is this within a temp state? It is in fact within a temp state. Right? Yeah, there's a temp alloc start right there. So we can do the present mode equals mem dot allocate. To continue on with size of Okay, present more chart pointer multiplied by present count. Yeah, a lot of this is grunt work, effectively. Vulkan being a very verbose API requires you to do a lot of grunt work. And if you try to make it very allocator aware and all of that, again, more grunt work. So no vector usage anymore, which means okay, there's no vector involved here either. This vector, I should be able to remove it. Frames are still vectors. So frame becomes pointers of the number of frames. There's a frame index. I need the swap chain image count as well. So uint32t swap chain image count. And the thing is that frame, oops, I forgot the pointer on this. Frames are also the same number as the swap chain image count. Like we make sure that the number of frames we create is the same number of swap chain image counts we create. So we don't need a separate counter for that. But here we do need the new things. So we have initialize until swap chain, everything else, frame index, except for frame index, will be allocated there. All right. And we're good to go from there. Let's see if this gives, yeah, there it is. Corner, and corner. Okay. Pointers are not compatible. Cons, pointers, and pointers are two different action things. While the above are fine. Okay. Here down initialize ones. So images will be swapped from images. Image views will be swapped chain views. Frames would be frames. Image count will be swapped chain image count. Again, grunt work almost. All right, let's move back. That's the constructor for this. We go down to the creation. So you see after swap chain, there's missing things. Swap chain images. Since the swap chain images was allocated here, it finished there. And so this particular object never made it out of the scope. So instead, swap chain images needs to be extracted out to this location. Same with swap chain views. So those have been manually added like that. So now we can do swap chain images, swap chain views. We need frames, which we don't have yet. We'll say to do, and swap chain image count, which we do have. Well, to do with. Something went wrong. 1 second. What's wrong with my string? Just checking something. The stream seems fine. It's probably just a bug in OBS. There we go. Okay. So swap chain views. Again, this was moved out, was to be handled. Swap chain image count similarly is supposed to be moved out. Swap chain image count, and we're done. Now, there's a bug here. It's relatively minor, but a bug nonetheless. I see capabilities.min image count, and that's it. But in reality, what I would like to do, so this is triple buffering. So option image count equals 3 means I want triple buffering. But if the min image count turns out to be 3, then ideally I would like one more than the min image count. Okay. So in the clamping here, I just make sure the min image count, instead of using min image count, I use min image count plus 1. Most of the times, the system will give us 2 as the min image count. So 3 makes sense. Otherwise, we need to clamp it properly. All right. So swap chain images, chain image count again. You don't even need to static cast, so that becomes swap chain image count. Again, this is frames reserved. We don't do reservations. And so we can just continue using it. Hold on. Here's the thing. This is a bug right here. This is a bug. This will bite us in the back very hard. We do a temporary allocation here. And this is a permanent allocation. Okay. So right after we're done using all the present modes, these need to go away. Folks, I'm from Earth. All of us are from Earth. Let's not. Let's not get into all of that. We're all from Earth. Unless you're an alien, in which case, reach out to me. I'd love to talk to you. Only if you're an alien. Okay, so these are now permanent allocations, guaranteed. Therefore, we can do the frames, which is also permanent allocation. So mem.allocate. And again, we can go for the size of frame multiplied by swap chain image count. That's frames. Frames is undefined. Makes sense. It's frame pointer. Okay. And this requires a reinterpret cast. The frame pointer happens there. Not equals count, which is nothing but swap chain image count. So we get that. Okay. Frames themselves have constructors, which we haven't invoked so far. So what we can do is we can just say this. And the this that it needs doesn't exist. So we have to go to frame and we need to figure out what it needs and what it doesn't need. Out of render device, it uses Q family index. It uses device. You can check and it does all of that. So what I can do is I can remove these particular things. I can just say it needs device. So const device and family Q family index for the movement 32T const direct Q family index. So we're just taking direct Q. For revision, direct Q is the only queue that can do everything. Well, it's not the only queue, but it's the only queue you use that can do everything. Create the declaration for it there. Okay, that's nice. That's fine. Now, there is a little thing with frame. Again, we're using constructors when all of these can fail. So these should also be a create function, right? But yeah, I think this is one of the places where I will be fine with not having perfect laws on the particular thing. Because if a frame fails to allocate because of semaphores, something seriously wrong is happening, and there's no coming back from it. There's no point in failing this particular type of initialization. So frames go in here and swap chain image count goes in there. Okay, that's fine. Now, another little property of having constructors that just take parameters is that you don't need them. Like, really, you just don't need them. I remove it, it will complain a little, then it will say, oh yes, because I have the remaining constructors, which wouldn't be happy. Fine, we'll add it back. Stop screaming. C++ compiler. Okay, we're back. All right, frames have to be cleaned up, but we don't need to destroy the memory. Image views have to be cleaned up. Again, there's no destroying the memory. Nothing else needs to be done there. Get number of frames. Yeah, this is just return swap chain image count. Number of frames and number of swap chain images is the exact same. Okay, build. Let's see what the errors are. There will be a lot. There are a lot. Always are. Swap chain image views is trying to do a for each. It can't because swap chain image views doesn't have everything. Instead, I create an std span with image views and swap chain image count. Manually add it. And include span and we're good to go. So all this will do is it will take a span, and the span allows us to just do a for each. Same with frames. It's a pointer. Again, this won't compile. So std span on frames and swap chain image count. That allows us to do a for each. Okay, what's your problem now? Again, so present mode is a array. Doesn't allow you to do a for each. I will just span it. So span takes present mode count. Cannot convert from int to surface image catcher. Or is that? Again, std span, surface format count. That's a span. Rejected solution. Okay, much less errors. Now, uint32 to int, bug prone narrowing, static cast, int. Static cast, int. So Insomniac Games actually prefers using the C-style casting, so this will be like SDL window cast over the static cast and reinterpret cast from C++, simply because the new version is more readable. The C version is more readable. It is a trade-off, and they have documented it quite well, and that's the only reason we're okay with it. So those are the kind of things we need to take into account. There's always trade-offs to everything we do, all the designs we have, and that needs to be taken into account. So now create render device is going to allocate its own memory. Init has been removed, I don't care. Begin not found for physical devices. std span, comma, physical device count. There we go. Begin, again, same thing. Okay, in this particular case, I'm already doing Q family indexing, right? I don't particularly care to, you know, the family index not equals to family count, and UFP equals key family properties index to key family index, right? No point actually doing all the span things here. Okay, where are we at now? Physical device in use, uninitialized local variable possibly in use. Okay, let's see. Physical device in use. Okay, null pointer equals null pointer equals 0 or -1 because that's a better sentinel value. Null pointer. All right. Destroy and init have been removed or whatever. I will move the definition out of class scope. Both init and destroy have nothing to do with needing inlining, while the rest, you can still make an argument about needing inlining. Global memory allocate unreferenced function. Ayo. Let the compiler handle it. Okay. Now, build GIB is on left state. Okay. We don't care about that. Let's run it. See if it runs. It does not run. Okay. What's wrong with this? Error shell model invalid device. Okay, what's the device? It is null. Why is it null? It took from render device. Where? In it here. Okay. What's render device? It is all null. Okay, where does this come from? So call stack create app state init comes from render device here. This render device comes from this one where everything is null inside it. So why is that? Create render device. Shit. So this is where it got from. We returned it directly from there. Why can it be a problem? Let's see it runs allocated. An instance, a surface, a device, a direct queue, all of these have actual values. Okay? So this goes in the new, we do the allocation. It still gets the right device and stuff. We will take a look at the destructor. That is one possibility. So because all of these are types, no, it directly went there. Didn't call the destructor. It went to the allocation. It returned here without going to the destructor. Is in it is true. So it is in it. And it does have values, you see? All of these have values. Now we go to allocate this data. Okay. Does it still have values? Looks like it. List data is doing a new allocation thing. Go inside it. No, it didn't go inside it, but let's see. Now this has null. This override. It overwrote. What does this mean? This means that my allocation has been overwritten. So the memory that was edited here, okay, inside render device, it took the global memory. It did the edits to that global memory. Those edits have been undone because some of this allocation somewhere. So here, do this allocation has not passed out through, has not been like properly modified. So let's see why. Okay. You create app state. We'll do another little thing. This is something definitely, let's call it not incorrect, but definitely something that should be improved. References, pass by references when you're going to modify is not very clear, so we should avoid it. Create render device, we'll fix that. But we'll fix that in a second. Again, you also take that. Yep. This is fine. Cannot convert from G memory to its address. We can do that for you. Word. You have no issues. West data allocation. Did a new on it. And the render device has become null. Okay. So this memory that goes in doesn't seem to get edited. We can do a little debug here. So auto state equals memory get state and we put a debug here. So void state is nothing but just making sure that the line is alive. Okay. So now here we can see that the state has value, it has this much size. I need to note this down somewhere now. We can just remember the last part, right? 7070, and this is 7728. Okay. 7070 and 7728. All right. What state now? 7070 and 7728. So between this point and this point, all the allocations have been undone for whatever reason. Okay. Let's look at the first allocation in this system. So there's a temp alloc start here. We can look at that. This allocation, we'll look at it anyway. So hold on, quit, run again. Debugging is fun. State 7070, as you can see, it's 7728. Temp alloc start hasn't been initialized yet. 7070 and 7728. When we try to restore the state, continue 7070 and 7728. Fine. There's another temp alloc start here. So initialize 7070 and 7728 again. We're not going to look at the restore. We will just look at this memory allocation here. Okay. So if we are right, this should be 7070 and 7728. 7118. Yeah, fair. Because frames and everything got allocated on this, right? And mem is at 7118. Fine. Capacity was 7728. Now it's 756E. Perfectly fine. This finishes that return memory 560. This is fine. Still 560, yes. Miscellaneous data allocation hasn't been done yet. What data did it allocate? 7718. All right. And memory is now at 7224. That is also found. Miss data is trying to allocate itself on that memory, and that rewrites send the device again. Isn't that fun? It re-initialized that location. Let's see that continue. So you go in here and get a shorty when the device started. Hmm. Well, debugging can be a pain sometimes. Let's do a thing. Let's use the brilliance of having a nice little, custom allocator. SDL log info. So we just log in info. Yep. Add it, please. So SDL log info. Category SDL log category system format percent. No percent required. So what we want to say is alloc percent p and percent LLU, percent p for the memory and percent LLU for the available. It should be fine. Void pointer, the interpret cost, void pointer. Okay. So this will print us that it allocated this, and I'll add the range to it. So available went from, as LLU, sorry. Memory went from this location to that location, where it goes from rectval to memory. So rectval dot reinterpret cost void pointer and comma there. Okay. Every time it allocates, it will tell us exactly how much it allocated. Similarly, when we get state, we will log saying state or hold on, temp, and you just say the location and the size because there's no rectval to temp. And when we restore, we will also paste that. We'll just say restore. Okay. Let's look at it, shall we? Remove the debug points. It's all going to be printed. We're just going to look at the print. Okay, cool. This is done. No printing has been done here. Build solution, up to date, build clean solution, build solution. And now it did not print. SDL log value seems to be much higher than info. So I suppose in blaze.cpp in appinit, there's probably SDL log level set log priority hmm, let's check SDL print log info. Okay, log critical, etc., etc. Category log. All of that is fine. Priority info, log priority. Let us set log priority. Log priority in category SDL, log category system, SDL, log priority info. So all the system will print info level stuff. Cool. Let's see. There it is. Temp. So it's stored 8070 on temp. Stored 8070 on temp. Allocate this much. Okay, 8070 to 8080. So that's 10 bytes. Temp is, I should probably print. I'm just going to fix that first. So inside allocate, I will also print how much you printed. And that data is still available. To send you again. So after memory, that should be size and we're done. So what is it now? So it's stored 16 bytes. Yes, that's correct. Extent. 144 bytes alloc. It is stored. So this is the temp that was stored here. So you can see these temps, even though it's stored multiple times, it never restored them. This one got restored here. Alloc 3080. It got restored. Outer one got restored. This is the next physical device. Okay. This is the last restore from 3 to 3PO. It's taken a 10 here. It has allocated to find color spaces. Done the restore. It has allocated 0. Why? Anyway, 3070, 3088, 3088 to A0, A0 to 118. 118 to 118 did a 0 allocation. I don't know why, but okay. And then it does this. So these are all allocations. These are all incremental. There's nothing I can say that says is overlapping, right? Like 118 to 268 does not overlap with that. It does overlap with this. It allocates 0. Why does it allocate 0? Seems like I forgot something in my allocations. Okay. There. Nope. Nope, that's not it. We can just put a nice little debug point there. Restart. Run it. Okay. How much did you ask for? Size is 16, 144, 120, 40. Actually, I don't care to be here. So we just stick there. Down there. Now go inside. What size did you ask for, friend? 96. Alignment asked for was 8. So I guess there's a problem with the calculation here somewhere. Address is 270. So found offset was 0. If it's equal to 0, then just go to allocate. Checks if size is fine for us. Size was 0. Why? There's the bug. You don't allocate found offset, you allocate size. Okay. So far, so good. We fixed one bug. We have one more bug. This is normal. Entirely normal. Does it say anything to us? It does not. Hey, David, what happened? Let's turn on configurator. This should have been running all the time. This should be running all the time, but it's fine. We will take what we get. So fences must point to valid pointer to an array of fence count valid fence handles. Okay, wait for fences. I asked for one. I asked for frame ready to reuse, which is a null fence. This fence is null. So why is it null? Did we create these? Right, that's the question. Did we create these? All of these are plain data. So creating the frames through this should lead us to the result. Where's the fence? BK check happened. So it should have been fine. Let's run again and see. Okay, frames. Each of these has a value to it. Okay, we're gonna just look into peep into it one more time. Frames, image ready to reuse has a value to it. Miscellaneous data, app state, initialized. Okay. App state returned. So that is again should be the correct app state, generally. So it's correct. Yep. Same value. There's app state in it. It is. So we continue. We don't care about this. So we get here. Okay, app state. So again, we check the render data has the correct values inside it. And it does. Frame index is 0. Current frame is the correct value, should be the correct value. Wait for frames. Frame ready to reuse the correct frame. Okay. Go back there. Take a step. Frame index is 1. Let's see what the value of the current frame is. It is nulls. It is incorrect. What is a possible thing that has occurred? Answer is I probably forgot to allocate the right number of frames. Did it happen? Size of frame multiplied by frame. So it's an image count. And it's the correct number of frames. This is the correct number of frames here as well. So yes. So this is one of the places where it is nice to use containers and things that have, support for proper allocation stuff. But, well, we haven't tried that. Okay. This frames. Let's got to it. I think I'm gonna close that first. Close this, run it. Close the Vulkan configurator, run it. All right. Now, short-chain image count is 3. This will do an allocation, step over, that 120, allocation of 120, right? Until 118. We do a new in this. So, frames, there's the problem. So, frames here is a single array allocation. We are trying to do an allocation on this frame and we're not moving it forward by the acquired value. Now this should work, at least for the frames. I mean, it should do. There is one more bug. We'll come to that in a sec. Okay, when you close it, it should crash. It did not crash yet, but it will crash. There we go. The reason for this crash is because an render device. Okay, first assert so not is invalid. So we just have to check if this cleanup has been called or not, because the cleanup has to be called and we're no longer going to be using the unique pointer anymore. Because inside render device, we use unique pointer, not render device. Sorry. Inside app state, we use unique pointer for render device. Mostly it was used because of default initialization requirements. But since we don't need that anymore, we can remove it. So inside cleanup, we do the cleanup for render device. So that shouldn't be a problem. Close it. Still does an unknown block. Where did that come from? Delete, destroy, memory. Okay. This memory is far forward from the memory we started with, right? This is not the original memory. So data pointer or like byte pointer original memory equals memory minus capacity plus, so minus capacity minus availability, right? This capacity minus availability is the used. And here, so this should just do original memory. And we can then set memory equal to that item manually. Yes, you can be paused. That was it. And it's fine. Okay. It worked out. Cool. We will just remove the log category from info log category of the system. Saves us noise. There you go. sRGB found. Okay, let's check. One render desires. sRGB. This CPP file that we will. That was space sRGB. This is just SDL log. It should be info. SDL log category GPU. Okay. I'll do the same thing for every single log in this. So SDL log, for every single SDL log you see, replace it with SDL log info with SDL log category SDL log category GPU comma. Find, replace, there's one extra bracket. Okay. Find, replace. No more occurrences. Replace. And this goes away. Cool. Triangle is still triangling. Now, we'll move on from the triangle itself. I will just do a get. So that's using custom allocator, connect all, Solution Explorer. Okay, fine. Now that you're back here, we will just get in the entity system. So what is the entity system? Well, actually, first let's get the triangle settled in. Right now, the vertices of the triangle are hard coded into the triangle itself, right? The shader itself, which means we cannot move it. It will always be at the exact same position on the screen. And it will always be this same triangle with the same color. Of course, that's not how games work. They do not write one shader per model. I mean, what's the point of a program if you're going to hard code everything, right? So this needs to be provided to the GPU from the CPU. And to do that, we need to create a vertex buffer. A vertex buffer is a buffer that contains vertices. I know that sounds like a duh moment, but one has to say it when one is dealing with people who might not know it already. So that involves having a buffer. Okay, so VK buffer, vertex buffer, something like this. And also we'll have one buffer for transforms. But okay, anyway, we will come to that. This VK buffer, if we create it like this, we also need a memory to it. So it's VK memory allocation. No, VK allocation. Buffer memory. G. Okay. Anyway, point is, we don't use this. People in the industry don't use this. Nobody really wants to use this. Okay. What people use is known as Vulkan Memory Allocator, VMA. Let's see if it is available on VC package like that, but I will actually just check it. VC PKG, search for VMA. There. So that's Vulkan Memory Allocator. Hey, Vulkan Memory Allocator HPP got an update. That's new. But we are using the C version, so we don't care. So we have to install this. In fact, we just need to copy paste that in. So we copy paste Vulkan Memory Allocators there. Build solution. That's it. Okay. It has cloned it and everything for us. Inside render device in the H file. After where we have device, the actual device, I make a space there. We don't need any packing anymore. These two will pack themselves actually. And this packs between itself. So we don't care. After device, we also need a VK, so VMA allocator. So VMA is this library, Vulkan Memory Allocator. I think it's by AMD. It's part of their GPU open program. So VMA / VK Memory Alloc. Okay. Has to come after volt.h. And there's VMA allocator because of it. I'm going to call it, I'm not just going to call it allocator because that can be confusing. So I'm just going to name it VMA allocator or GPU allocator because VMA is Vulkan Memory Allocator. DirectX also has a DX allocator. So I'm just going to call it GPU allocator. Okay, now VMA allocator, GPU allocator, and that is exactly as it was. Nothing really changed. This, on the other hand, needs a change. So it's right after device. Done. Formatting. Oh, formatting. I need to set up client format at some point. The device goes into GPU Like after device comes GPU allocator. So there we go. Okay. Now that that is done, this is forced to use the GPU allocator, which will be right here. So GPU allocator. Again, that needs its own creation. So we will go back all the way to where we created device. While it doesn't matter, while we could create VMA allocator almost at the last moment before everything else, because that is the order in which we have written the values, it's best to also do the allocations in the same, not allocations, but like initializing in the same order, just because it becomes easier for people to track. So VMA create allocated. Okay. What does VM? Okay. Well, VK check is actually causing a bit of trouble when it does a macro expansion. Okay. VMA create allocator. So it takes create info just like anything else. And it takes the allocator, which is GPU allocator. Okay. This will be VK check. So VMA is made in a way that it actually returns Vulkan results, the VK result object. Quite nice, eh? VMA allocator create info first allocator create info equals. I think let's start and here create this. Okay, now flags 0, physical device in use, device, preferred large heap block size. Yeesh. VK API memory, VK API version, VK API version 1.3. External memory handle types. I don't know any of these. So we check it out live, as one should. Create info struct, physical device, preferred size of a single device to be allocated from large heaps, optional. The allocation callbacks, optional. VK allocate memory, free memory, optional. Use set to 0 to use default. So set to 0 to use default. Allocation callbacks. CPU allocation callbacks, optional. And be null. So null it is, just like every other allocation callbacks that we have. Then device memory callbacks. So here we will have a little bit of a difference. Because we use Vulk, Vulk has tables, right? Different tables for different devices. So we actually need to get the Vulk functions. Need to get the Vulk functions in order to get the function pointers. Device memory callback. We'll just leave it as it is for a second. It will fail, but we'll see. Oh, right. This again is optional. We'll leave it to null pointer, heap size limit. VK hole size. Vulkan functions. These are necessary. And external handle types is also, I believe, optional. Either null or a pointer. So null it is. Okay. P Vulkan functions can be necessary if you're using Vulk. Pointers to Vulkan functions. And yeah, it does need that. Okay. So VMA Vulkan function needs to be created. Vulkan functions. And it moves all of those. Oof, those are a lot. So what we will do is we'll look at Volk documentation. If I remember correctly, VMA. Hmm. Volk with VMA. So the cookies only need to provide all of these functions, and they have to be done manually. Yay! We can get inst proc address. What I'm going to do, I wish I was using Emacs. It's just much simpler than that. But really VS Code in this particular case. So the only reason you have to do this is because the actual functions, instead of being loaded as real functions by linking to a library, these functions are just function pointers that are assigned to by Volk at initialization. The benefit of this is that you don't link to the Vulkan library, which means not having Vulkan doesn't break your program. That is a valid problem. Let's say if you're on a Windows, not Windows, if you're on a different console device where Vulkan may or may not exist, but you do use Vulkan. Let's say Switch, for example, right? Nintendo Switch has Vulkan support. So maybe you have Switch, maybe you don't have Switch. So maybe you have Vulkan, maybe you don't have Vulkan. You don't want to depend on that. So this is one way to do it. And you don't want to depend on which Vulkan either. Also, meta loaders make it a bit faster because you don't have to go through a virtual, it's not a virtual function call, but it's kind of like a virtual function call because it has to do a switch through the functions that are available. Let's not get into the implementation details of this. It's normally a pain. Okay. That's that. Get memory Win32 handle cache. Yeah, we don't provide that. Low 32 bit. Okay. So P functions has been provided. VK whole size has an issue. Null is fine. Null pointer it is. Okay, so it takes that. GPU allocator. Now that will be outside right there alongside device. VMA allocator. GPU allocator. So far so good. That should just work. It will have an issue because we did not. Hold on, what happened? Unresolved symbol VMA create allocator has been found. Makes sense. So the way it works, just like Volk really, even though we have linked to Volk, I believe, and we did. VMA normally requires you to declare the VMA memory, right? Or the implementation of VMA because it's all header only. So we need to define these to 0. Oh, this is a really nice. Come on. That's terrible. Should have checked the documentation there. So, okay, we need to declare those first at the top somewhere. Again, this is a minor not issue exactly, but a minor thing that we need to fix, which is all of these configurations that I'm doing right now. They should be somewhere in a common and separated place, like a global utils or something, where they'll automatically configure these things. So the PK functions, okay, and VMA role import functions from role that says VMA allocator create info. So it needs the allocator create info. It needs a VMA. That's a very unique situation. Full initializes the destination root functions from this. Initializing all root. Yeah, done. Fill in this thing, done. Create instance, done, and that. Cool. So VK, check. VMA import functions from Vulkan, takes allocator create info as a reference, as a pointer, and VK functions as a pointer. Whatever it does, we particularly don't care. Attach the functions. So I take that as an input and then I have to attach it. So allocator create info dot p Vulkan functions equals VK functions. In that fun. And that's not called anymore. Because that is something we didn't do. So this is a null pointer now. That is entirely gone. Right? This is directly something that we take out from and we give to the Vulkan library. And lastly, once this is done, we also need to make sure Vulkan has loaded. So Vulkan load device. Build unresolved symbols. Still need to check out that. Okay, enabling extensions. We will look at this because we do need this particular extension, but later. VM implementation, see? So in one source file, so add new item, class C2P file, VMA implementation, add. So in this VMA implementation, we will just do that. We'll also include bulk, because one has to. I don't want any possible cases where VMA includes the wrong welcome. Okay, 8. Component insert specter mitigation. That is causing so many pragma push. Suppress warnings. MSVC, suppress warnings. C++. Because we don't want this, right? We don't want it to. Okay, push warning, pragma warning, push pragma warning, push suppress pragma warning. Oh, build. That didn't work out. That didn't work out at all. Spectator constant found suppress. All right. What did I do wrong? So pragma, suppress and justification. Suppress. Let's see an example of suppress. Okay, push. It should be something like 0 then. So no warnings. Give me no warnings. Oh, come on. It's 5045, right? Push. Suppress. Pragma. Warning. Push. 1. Suppress. 5045. Build. Acting to account. Can disable it. Wait, did I read the documentation correctly? Yes. Build it. Let's see what happens. Okay. No more warnings. Still have our triangle. Things are fine. And VMA is now in use. Cool. So what's the next step after we get VMA? We need to create device. We need to create the buffer that we want to use. So this vertex buffer here. This VK buffer will soon be not so good anymore, but for now it's fine. Allocation. So we'll add that. It is below Volk, so it's fine. You see this will keep happening. This needs to be placed in a single place where we don't have to make sure the order is correct at all times. But for now, it's fine. Okay. Vertex buffer, we take a vertex buffer allocation. We have the pipeline creation there. So we'll go in here. Okay. Now, few things need to be added in here. So those few things we will add, but later, which is this vertex input state, which we have left to null pointer because we don't take any input right now. Once we do the vertex buffers, we will be taking inputs. But for now, we don't care about that. What we do care is the data that we have and how do we upload it to the vertex buffer. So once all of that is done, we create total mesh data, create like a vertex struct. So struct, vertex, it has a float array of position. So position, which takes 4, as a float color, which takes 4, and that's our vertex. Okay. I'm not using a library right now. I'll probably decide and integrate it later because there are two options. One is GLM, which is built more or less similar to OpenGL. And then there is DirectX Math library, which more or less is similar to DirectX. Since we use Slang, which uses the DirectX-like notations on the shader side. So instead of a vec4, it says a float4. I'm more oriented towards using something that looks like XM float 4, which is the DirectX version of it. But for now, we leave vertex like this. However, we'll get to this later since it's been a long stream, I believe. And yeah, so have a good time. We will next time get into creating a vertex buffer to set up a scene. So good day. See you later, guys, gals, and non-binary pals.